we're going to meet some of our old friends again. So remember regularization and validation? They apply to neural networks. Surprise, surprise. Foundations are here. Okay, so on the left is the overfit, very simple 10 hidden unit neural network. Okay, and on the right, I'm showing what happens when we use a little bit of weight decay. Remember we studied weight decay when we did regularization. So we defined the augmented error. E augmented is the in-sample error plus lambda W transpose, lambda over N, W transpose W. Well, in our case, that was when we did the linear models, we had just one perceptron. In our case, we have, matrices of weights. So in our case, we have W1, W2, and all the way up to WL. Okay, and so this is just the sum of the squares of the weights. So we can, equivalently compute E augmented is equal to the sum, is equal to the in-sample error plus the sum of the squares of the weights. So sum over I over L, so the layer I and J. So remember each weight connects a previous layer node I to the layer L node J of WLIJ squared. So we sum all the weights. And if you take the gradient, so the gradient of E augmented is equal to the gradient of E in. Okay, so there's a lambda over N, which I left out, plus lambda over N, the gradient of the squares, okay, which is just, so if we take the derivative, let's take the derivative of the augmented error with some weight, WLIJ, it's the derivative of the in-sample error with respect to that weight, plus lambda over N. Now this guy is just twice the weight itself. Okay. And so what this means is that the gradient becomes the gradient plus twice the weights. Okay, and so the derivative of augmented error with respect to the weight matrix WL will be the derivative of the in-sample error with respect to WL plus lambda over N, 2 lambda over N, WL itself. Okay, these are just the weights. Okay, and so, the update is WL, and if you're doing stochastic gradient descent, then it's just the in-sample error on that data point. Okay, but the update for gradient descent is WL. It goes to WL minus the gradient. Okay, DE in by DWL minus. So there's a shrinking term, 2 lambda over N WL. Okay, you multiply all of this by your learning rate eta. Okay, so that's weight decay. Very simple to implement. You just, you get this gradient from backpropagation, and this is just, an additional term that there's essentially no computation here. Okay. And on the right, I show you what happens with, weight decay parameter. The amount of weight decay, lambda is just equal to 0.01. Very small amount of lambda. Look, it gives you a very nice fit. Certainly not the overfitting you've got on the left. Okay. Let me show you another technique called early stopping, which applies in particular to neural networks, but anytime you're doing iterative optimization. I'm showing you the result of this technique, early stopping. It's an interesting technique that applies to neural networks, neural network training in particular, and you can use it whenever you do iterative training. So let's talk a little bit about early stopping. It's another form of regularization, but it results from an interesting view of what's going on when you train. Okay. So when you train, you start at some weights. Let me call those weights W0. Okay. And that's the collection of all your weights. So it's a very huge dimensional space. And you take one step of gradient descent. So you do one step of gradient descent. So you do a step of gradient descent. Okay. And that takes you to the weights. Let's call it W. Let's call this W of 0. So it takes you to the weights W of 1. Okay. Now, what's the idea behind gradient descent? The idea behind gradient descent is you're going to take a step and the gradient step, the negative gradient step, is the best step. Remember, we derived this. So the W1 is the best set of weights to go to among all the sets of weights that are inside the sphere of, this step size. So if I draw a sphere of this step size, then, these weights W1, okay, in some sense are optimizing, you're picking the best hypothesis in this set of weights. So you can think of this as a hypothesis set H1. Okay, nice. Okay, good. Now, let's see what happens when I take my next step. Well, I'm starting here and I take my next gradient descent step. So let's say it takes me over here. Okay, again, why did I take that step? Because it was the gradient descent step. It was the best step to take of that size. So if you look at all the possible weights that are in that sphere of that size, well, these are the best weights to take. Okay, so these are the best weights to move to. Okay, and effectively, well, this is the best set of weights in this originally shaded, set of weights, which you can think of, any set of weights is a baby hypothesis set. And now I move to the best among these weights that are now going to be shaded, in this fashion. Okay, so now I move to the best set of weights in that set. Okay, so in other words, this set of weights is better than this. Okay, and then that beats everything here. So this set of weights is the best in this union of hypothesis sets. Okay, so let me call this union of hypothesis sets. Now I've got a new, bigger hypothesis set. Okay, let me call that H2. Okay, and what have I effectively done by taking 2 steps of gradient descent? I've effectively searched H2, this bigger hypothesis set, and gone to the best hypothesis. So now I take a next step. I take another step of gradient descent. Okay, and that effectively searches, the ball around that set of weights. Okay, so this was W2, and this is now W3. Okay, and the ball of weights around that set, this is the best. So we've got a new winner. This is the best. So this beats this beats this beats this. This was the best in all of that, and this beats that. And this is the best in all of this. So this guy is the best in this new union hypothesis set. So if I define a new union hypothesis set as H3, so this guy is H3. Okay. Then W3 is a hypothesis picked from H3 that is best. I've effectively explored H3. So you see, with each step of gradient descent, I'm effectively exploring bigger and bigger hypothesis sets. So H1 is a subset of H2, is a subset of H3, is a subset of H4, and so on. Okay? And these H's are indexed by iteration number. So if this has a DVC D1, then this is less equal to D2, this is less equal to D3, this is less equal to D4, and so on. Okay, so what's the picture that goes along with this? The picture that goes along with this is, if I plot iteration number T, okay, then I'm picking the best and best hypothesis set in hypothesis in larger and larger hypotheses. So the in-sample error will be going down. Okay, and that's no surprise because I'm minimizing the in-sample error. But effectively, at each step, I've searched a larger hypothesis set. So, what's the link between the in-sample error that I've currently gotten to and the out-of-sample error for the hypothesis set that I've searched up until that point? The penalty I better pay is, this VC penalty that depends on the D VC for iteration T, omega of DVC for iteration T. Because I searched a larger hypothesis set. So this is sort of what's going on. Okay, and if I decide that I'm only going to, try hypotheses 1, 2, 3 up to 1,000, that means I'm trying I'm doing 1,000 iterations. And what will the E out be? It's the sum. We've seen this curve many times. This is the bound on E out. Okay, but now what this is saying is interesting. Okay, what this is saying is interesting. Don't train for 1,000,000 iterations because that explores too many hypotheses set. There are too larger hypothesis set. There's an optimal VC dimension. There's an optimal number of iterations to train for. Okay. What's going on here? If I imagine and typically what we do is we start at small weights. So if you imagine, I start at small weights, W0. Okay, and the optimal weights that minimize the in-sample error, let me call that W star. If I train forever, I will get to W star. And so that's the minimum. And so there are contours of constant in-sample error. Okay. Okay. And what's happening is I'm moving from W0 to W star step by step iteratively by doing gradient descent. Okay. So I'm implementing some trajectory along this, set of contours. I'm going from my start point to the optimal. And what this picture says is that there's an optimal number of iterations which balances the in-sample error you've gotten to plus the error bar you have to pay for the size of the hypothesis set you have searched. So, and this optimal T star, okay, is basically stopping the training early. Saying don't train forever and go all the way here. Stop when you get to some point here, W of T star. Okay. Stop the training early. Early stopping. Okay. Now, if you look at this picture, effectively what it's doing, usually we start at small weights and you need to go to some larger weights in order to minimize the in-sample error. By stopping early, effectively we are putting you at a smaller set of weights. So there's a link to regularization. That's why I said it's a form of regularization, but we call it early stopping. Effectively, we're saying, as you search more and more, effectively you've used a bigger and bigger hypothesis set, and you shouldn't go too far, because then you start overfitting the data and your pain and your E out is increasing. Okay? So there's an optimal number of iterations to train for. Okay? Don't minimize E in completely. Okay, now how do we pick this T star? Well, that's the problem. Okay? And so what we can do is we can set aside a validation set, our old friend validation coming to revisit us. Okay? And so we'll observe the training error going down on our training set, E train. Okay? And typically the validation error will sort of do something like that. Okay? And then that tells us, the validation error is telling is our sneak peek at the out of sample error. Is telling us that, you should stop training here, T star. Okay? And that's the left picture in the diagram there. So, and that's real data. That's the real digits data. Okay? No made up data, real algorithms running on real data. Okay? And real performance being delivered. So, with a training set, you train. Why do you need a training set? That's what allows you to get better and better hypotheses. Okay, so taking steps to get better and better hypotheses, but you're searching a bigger and bigger hypothesis set, and then the validation error at some point starts going, and that's basically saying that you're starting to overfit. It can be explained by this picture that we've seen many times. Okay, because you're searching a larger and larger hypothesis set, and by the validation, when the validation starts going up, that tells you when to stop training. So in reality, we train a little bit more, then we see the validation error going up, and we go back to the weights that we had at the optimal number of iterations. Okay, so you have to, in some sense, store, the optimal weights seen so far, optimal with respect to validation error. Okay. And then when you use those weights to classify, look how beautiful the classifier is. Okay, so that's validation, in particular used for early stopping. Okay, so, that concludes our discussion of neural networks. Okay, so, we talked about the derivation of neural networks, about how cascading perceptrons allows us all this power to fit. Okay, then we talked about fitting. Okay, how do you fit the neural network to the data? That was last lecture. And this lecture, we've addressed approximation versus generalization. You have to regularize. Okay, now let's spend a little bit more time on the second issue of the second step in learning with respect to neural networks, which is how to efficiently train, how to efficiently minimize the in-sample error.